Today it is very much a pleasure to introduce our speaker, Zaira Nazario. Just a brief background on Zaira. She is currently the Theory and Applications Technical Lead at IBM Quantum. And prior to being at IBM, she served as a scientific consultant to DARPA and IARPA, which is, I think, first where we crossed paths during some IARPA programs, advising on strategic technical investments focused on superconducting quantum information technologies, advanced navigation, communication, computation, and sensing. Dr. Nazario has worked shaping science policy at the US Department of State, where she was also launched and managed R&D programs in biological, chemical, nuclear safety, and security. She held an appointment at the Max Planck Institute for the Physics of Complex Systems. This is addressed, correct?
That's
right. That's right. Very beautiful spot, especially after they rebuilt it. It's quite nice. Investigating quantum criticality and emergent physics in condensed matter systems, she earned her PhD in theoretical condensed matter physics from Stanford University, where she focused on quantum phase transitions and uncovering the physics of strongly correlated systems, including superconductivity. So it's an absolute pleasure to have you here in the AQT colloquium, and we pass the microphone to you for your presentation. So please share your screen as you like.
All right, let's see. Thank you, Irfan. Can you see my screen?
Yes, looks good.
Right. All right. So this is going to be likely a different talk from what you normally hear in this colloquium, because instead of discussing just one topic at length, what I thought I would do is give you a high-level picture of sort of a potpourri of activities that are going on at IBM and on theory and applications, kind of like to give you a flavor of the research that we've been doing and an idea of how we've been approaching things. So the theory team covers 6 areas that are focused on generating insights to demonstrate the fundamental difference and benefits of quantum over classical computing, and then the discovery of quantum applications to show potential, the potential of the technology. So we're building and quantifying candidate quantum circuits for demonstrating quantum advantage, and optimizing them and reducing their complexity while trying to maintain as much of their essence as possible, then developing new algorithms from them. Running a lot of those circuits requires performing pretty high fidelity operations. So that's a capability that so far we only know how to achieve using quantum error correction, which is why you see error correction at the base of everything. The near term, while we get to error correction, we improve the accuracy of the solutions that we're getting from hardware using error mitigation techniques. The algorithms that we develop must be translated to games in practical applications. And for applications, we're focusing on 6 domains: physics, chemistry, machine learning, optimization, and finance. And then all these aspects are incorporated in demonstrations that encircle everything, and they introduce new techniques or that prove the value of quantum versus classical. So the results in all these areas are then transitioned to clients, and our partnership with them is really what informs the application that we pursue, relevant to science and industry. So the goal in this next 45 minutes or so is kind of like to see an example of 2 or of work in each of these areas. So starting with error correction, this team is led by Andrew Cross. And I imagine that a lot of you have different levels of familiarity with error correction. So I thought I would start by very quickly refreshing your minds about what it is and why we do it before then going into how we're doing it. So we have several candidate algorithms to run with theoretical evidence for an advantage over classical methods. But running them at the scale that we want to run them requires millions of gates, or even much more than that. And while executing those gates, those millions of gates, we will see bad things happen. We'll see the coherence of the qubits. Those will lead to errors in 2-qubit gates that are proportional to gate time and inversely proportional to T1. Now you'll see over or under rotations, things like crosstalk and other systematic errors. And so while we may hope for not too many nasty things to happen, it is a law of nature that anything that is not prohibited is mandatory. So there will be lots of errors and they will accumulate. Now, if 10 to the minus 4 gate fidelity seems daunting to achieve, then something that lets you run trillions or quadrillions of gates seems unlikely with physical qubits alone. But by encoding, say, k logical qubits into a larger number of physical qubits, and running circuits that allows you to detect errors by measuring some ancilla qubits. Maybe you need to use some extra information from additional qubits that we call flags, then we can correct the error. So that's how error correction codes give us, in theory, these long-lived qubits and higher fidelity gates, more than is possible from the individual physical qubits. It's a concept very similar to that of classical codes, just that you now have to deal with the quirks of quantum mechanics. So as an example of how it works, if you have a physical circuit composed of operations with error P, that circuit will fail with a probability linearly proportional to the error rate of the physical qubit operations. But if instead you implement quantum error correction, then that error corrected circuit will fail with probability that, in this example is square, but in general is proportional to a positive power of the error rate of the physical qubit operations in the asymptotic limit of small error rate. So that shows you how powerful this can be in reducing the output error of your circuit, because the error that comes out is a lot less than what comes in. We then see that it's possible to build a system that can perform an arbitrary quantum computation, provided that the error rate of the physical operations in the circuit is less than some constant value. That's the threshold value. And as long as you are below it, we can make logical or encoded circuits arbitrarily close to correct. And the overhead of doing that is at most polylogarithmic in the accuracy that we want in the computation. So in the plot on the left, the different colors correspond to different sizes of the error correcting code. That's the code distance. And you see marked by the green arrow that the logical error rate decays exponentially with the code distance in the subthreshold regime. So if the physical error rate is higher than the threshold value, the extra overhead means that the errors will happen faster than we can correct them. And at that point, we're better off with the unencoded circuit. But even more important to focus on is the black line that we call pseudo threshold, because that marks the physical error rate below which the encoded qubit outperforms the unencoded qubit. So at higher, the higher the distance of the code, the more errors that we can correct. And in general, a distance D code corrects any D-1/2 errors. Now, in going from our first system to the latest Falcon devices, we changed the underlying topology to a sparser lattice in the shape of a hexagonal ring. And the reason is that our systems use fixed frequency qubits. The characteristic properties of the qubits are set at the time of fabrication. And because of fabrication tolerances, then the frequencies may deviate from the desired values. So when the connectivity is high, that leads to frequency collisions. Now we could remove them by applying, say more microwave controls, increasing the length of the 2 qubit gates, but we want to avoid that because that's not scalable. So for about, say, like 15 to 20 megahertz precision of setting the frequencies, going to the hexagonal lattice led to zero collision chips, about 10 times more often than using the square lattice. So then the theory team was given the challenge. Okay, so what's the path now to fault-tolerant quantum computing with this heavy hexagonal lattice? And so, well, challenge accepted. And what the team did was they developed what was a new code that combines some of the features of the surface code and the Bacon short and matches the engineering constraints that we have. So if you want to correct D/2 errors using this code, then you're encoding qubits in a patch of these square qubits. But you need some extra qubits to implement the error correction circuit. We'll see that circuit in a moment. And in the end, you're looking at about 5 D²/2 qubits to encode a protected qubit. To do a control NOT gate on 4 logical qubits, you need about 10 D² qubits. So this is the beginning of an ongoing line of research that is aiming to co-design the hardware and the error correction, where we're taking the engineering constraints to heart, and we're trying to design codes that match those constraints. Now, the other direction is one where theory informs the hardware that we will need in the future, and we're pursuing that long-term. We'll see some examples of that as well. What we're doing here is really working at the intersection of those devices that we can realistically build in the time frame that we set up, which is pretty aggressive, and then the ability to innovate on the error correction front. So in order to do the error correction, you need to measure some polyobservables on multiple qubits. So those are shown as the red and blue squares corresponding to X and Z type measurements that you see on the right-hand side. So this work was done by Andrew Cross, Wanyu Zhu, Ted Yoder, Chris Chamberlain, Jared Hertzberg. The circuit on the far right for the blue checks, that's pretty simple. And it measures two bodies Z operators. So we measure this and then we combine the results into surface code stabilizer checks that behave as you would expect for the surface code. And then the one for the red checks in the bottom is a little bit more complicated to measure. And the reason is that in part that because of the heavy-hex connectivity, we want to mediate connections between the yellow data qubits and the black ancilla qubit in the middle, because the black is where we're going to read out the eigenvalue of the operator. So to do that, the team used the interactions through qubits 5 and 6 to get more information about which errors occurred, and then built that into the decoder, and that helped improve the error rate overall. So these weight 4 checks are then combined into strips by multiplying the results, and those are used to detect in what column the phase errors have occurred. Now we have the error correction circuits. We know that they're fault tolerant, but we want to understand better how they might behave under more realistic assumptions of noise. And those simulations are hard, but they give us a sense of the hardware and the software requirements for demonstrating error correction. So the team is doing those simulations right now, and they're investigating things like how the code behaves if you choose your X or your Z stabilizers to be surface code-like or the Bacon-Shor-like circuit. Then on the left hand in here, you have some of the requirements that we believe that we would need. In particular, we're investigating the level of crosstalk that we can tolerate with this code and how to improve the code and make the circuits fault tolerant to crosstalk as well. Then of course, we need to figure out how to do computations with this. And so the team had to discover how to do a set of fault tolerant gates for this code. They did that, and they're now looking at how those gates perform under different noise assumptions. Now in these plots, you have simulations of the error rates for this code. If you look at the error rate for all the operations, and to simplify things, take them to be equal, the error rate for bit flip type error, that's what you see on the left side. Those are detected by the surface code like checks, and it has an asymptotic threshold of about 0.45%. So it's not that much worse than the surface code. Phase flip errors are detected by the Bacon-Shor type check. That's the one on the right. And once you get to 10 to the -3, then increasing the code distance begins to improve the logical error rate. If you are below 10 to the -4, then that error rate drops pretty dramatically as you increase the distance. So, low logical error rates can be achieved for physical error rates on the order of 10 to the -4. This is ultimately part of the motivation to choose Condor to be about 1,000 qubits. This is the plot of the resources for this code. And a machine of this scale would allow us to test pretty much all the fundamentals that we need. If you focus on the blue line with this 1,000 qubit machine, we can look at a single logical qubit up to a distance 19. And to do some significant large scale applications, we think that we need to be somewhere between distance 11 and 15, somewhere around there. So in terms of demonstrating a 2-qubit gate at 1,000 qubits, we have the resources to look at 4 distance 9 qubits with enough connectivity to do logical signals. But we need to be able to do more with the qubits that we have. So the question is, how could we do that? All right, so let's think about the problem, right? The restriction that comes with topological codes like the surface code is that the ratio of the number of logical qubits to the number of physical qubits decreases with the code distance squared. And this is related in part to the locality of the stabilizer measurements. And that leads to prohibitively large resources required for their implementation. Now, the problem could be addressed by developing constant rate quantum codes where the ratio, that ratio is constant with respect to the code distance. But implementing constant rate codes require non-local stabilizer measurements. So that means removing the restriction of only nearest neighbor connectivity, and now we'll need to use long-range interactions to encode more qubits into n physical qubits as opposed to just 1. Another alternative is look at higher distance code, but that's related again to having long-range connectivity. So we're exploring a variety of fundamental research projects with the potential to reduce this cost. Like for example, Ted Yoder discovered a graph-based formalism for surface code using certain defects that are called twists, and that allows you to reduce that constant that is in front of the d square So you can encode logical qubits in fewer physical qubits. And this framework includes not only surface code, he found new examples of codes and is able to systematically explore codes, adding a little bit of non-local connectivity, or where you have like some extra long-range connection, and then ask, what does that buy me? The 4D code of Thomas Joachim O'Connor builds on work that showed that the 3D surface code has a transversal gate that is outside of the Clifford group. And then from there, it was shown by Ben Brown that you can take one of those space dimensions, turn them into time, compress it all down to the plane, and then get a compact gadget for doing a gate. So now the fact that from 3D, you get a new gate in 2D, it's pretty interesting. I thought it was pretty remarkable. And it suggests that there might be ways to break space and time. And this is what this work is studying. The team is, what they're doing is exploring the conditions that would be needed to implement non-Clifford gates in a similar way, and then looking to see how you can use these to do addressable logic in 3D codes, for example. So this is important for implementing fault-tolerant gates in codes that encode many qubits and hence reduce the space overhead. Remember also that, you know, like one of the problems with the standard surface code is that magic state distillation is pretty expensive. It's about 99% of the overall computation. Right? So you want to search for non-Clifford logical gates, avoiding the cost of magic state distillation. And so this is one way to do that. Another way is to stay in 2 dimensions, but go then beyond the stabilizer formalism and abelian topological codes, and then look at things like 2D non-abelian topological codes, where instead of magic state distillation, you then use braiding of non-abelian anyons or of some topological defects to implement universal fault-tolerant gate sets. And that's the work of Wan Yu Zhu that you see in the bottom left. Then work done by Muyuan Li and led by Ted Yoder looks at 2 families of codes that also encode many qubits. One is an efficient version of a code family discovered by Sergei Bravy. The other one is something called hypergraph product code, which is another code that, again, it's encoding many qubits. So those are some of the leading candidates for reducing space-time costs that we have right now. In that case, what they did was implement 2 small examples of those codes and then the decoders for them, and they studied their circuits. And they show that if you get error rates around like 10 to the -4, then these codes outperform the surface code and other codes. So they're pretty much a denser encoding of information than the current codes that, you know, are kind of like more popular. In all these cases, what we need, of course, is to understand the extent of the long-range interactions that would be required. We'll need to understand the fundamental limits on the code parameters and learn about all the implementation challenges. Now, from seeing how we use circuits for error correction, let's see now some examples of how we've been using circuits for algorithms. And this is an area that is led by Kristen Tem. In looking at algorithms, we try to focus on categories of BQP complete problems because those are, you know, the ones that are hard classically but can be solved efficiently in a quantum computer. So in particular, we have quantum simulations. You're familiar with these, simulations of materials, chemistry and physics. We have algebraic problems that include solving systems of equations and problems like the discrete logarithm. And then quantum search and walks that include things like amplitude estimation or graph problems or some of the algorithms for optimization problems. So while we succeed in error correction in the near term, we have to do something. So we rely on scalable methods to mitigate the effect of errors in the solutions. So for gate errors, many of the algorithms and applications really depend on average quantities. So because of that, the team could develop a clever way to run circuits multiple times, then amplifying the noise rate by some multiple each time, computing the mean value, and then using the results to get a polynomial boost in the fidelity of the solution. Maybe you're familiar with these, but maybe I should expand a little bit there. So in essence, you know that quantum circuits can be expressed in terms of evolution under a time-dependent drive Hamiltonian. And you can expand that Hamiltonian as a series of n-qubit poly operators. Then the expectation value of an observable for a state that is prepared with that drive in the presence of noise, you can expand that also as a power series around the value in the absence of noise. So what all that means is that if you can run the experiment multiple times and then amplify the noise rate by some multiple each time, then you can use the results to suppress higher order noise terms and then approximate that way the zero noise expectation value of your observable. The problem is that amplifying noise rate in general is challenging experimentally. I mean, you could think about things like inserting noisy gates in the middle of the circuit, but that requires having a pretty good knowledge and assumptions of the noise mechanisms that are present. Of course, we want to avoid that. So what we notice is that if your noise is time translation invariant, then amplifying the noise is equivalent to rescaling the drive that you use to evolve the system. So this allowed, this is what the team does. It allowed results, for example, for the original simulation of lithium hydride to improve by about 10 times. In the case of measurement, we want the result of ideal measurements, but you have noise, so that distorts the outcome. That noise can be described by a matrix of transition probabilities from the ideal to the noisy outcome. And to capture then correlated without errors, capture crosstalk, the team introduced a correlated noise model. You can then calibrate the measurement using well-characterized input states to learn the parameters of the noise model. And once you have knowledge of the error affecting the hardware, that means that you know the noise matrix. And so you just need to apply the inverse matrix to the noisy measurement outcomes using a sampling algorithm to estimate the ideal ones. They used a continuous time Markov process as the model to resample and then predict what the measurement would be without crosstalk. So in the plot, you can see the improvement in fidelity when we use measurement error mitigation versus the raw unmitigated data. This was applied to up to 12 qubits for a highly entangled GHZ state, up to 20 qubits for circuits that didn't have as much entanglement, but that was because we were limited by the fidelity of the gates. But in essence, it shows a scalable way of mitigating crosstalk errors, having knowledge of the hardware. And that one is also available in Qiskit. Okay, so now the question to ask as we think about how to use all these near term is, okay, so how do we identify quantum circuits that are hard, and can we do something valuable with them? So the few problems that we know so far either sample from probability distributions from which classically you cannot sample efficiently and accurately, or ask to extract hidden features of certain structures, for example, the hidden shift problems. And most of the algorithms that are used to solve them really sample from the Fourier spectrum. These circuits, they can be related to the estimation of transition amplitudes and correlations. So in the case of forrelation that you see here, it's asking, are two Boolean functions independent, or is one correlated with the Fourier transform of the other? And so following this line of thoughts, Christian Tem and his collaborators worked from a circuit that is closely related to that of correlation, which we know is hard for a conventional computer to solve, and then used it to construct classifiers with complex higher dimensional quantum Fisher maps. So the method essentially uses a circuit to map classical data to a high dimension Fisher space, then takes a hyperplane in that Fisher space and rotates it into the right direction to separate the data. Now, to have a quantum advantage, you need a Fisher map that gives rise to a kernel that's difficult. And so a good candidate to use is anything that has to do with Fourier sampling. The key observation here then is that that the only way to make this process non-trivial is to make it hard to evaluate the kernel classically. And two, that for a quantum computer, estimating the kernel becomes simple because it is essentially an estimation of the transition amplitude of the circuit as an inner product calculation. So you see in the slide the circuit that is run to directly estimate the kernel that is used to implement the classifier. It's layers of Hadamard followed by diagonal gates. So you start with 0, you run the circuit, you invert the circuit for different data points so that you're basically measuring the inner product efficiently, and then feed the results to a classical optimizer that gives you plus and minus, and use that to find the support vectors to classify the data. So if we didn't have access to the diagonal gates and instead had a box that we can't look into, and if the function in the correlated circuit that we saw in the previous slide was plus or minus instead of having phases, then this circuit becomes the threefold forrelation circuit. And now the open question is whether we can find interesting quantum kernels and Fisher maps for data that has some kind of structure where we could have quantum advantage. And in fact, just a couple of weeks ago, the team posted on the archive a paper where they identified a quantum Fisher map and a circuit for kernel estimation with a formal proof of advantage over all possible binary classical classifiers, meaning that the classical algorithms cannot distinguish the classical data points from having random labels, while the quantum learner can recognize those classically intractable complex patterns and achieves high accuracy in the separation of the data points. So in this case, the circuit is related to the discrete logarithm problem. And I believe is probably the first formal proof of advantage for a machine learning process. You can find the details in the archive reference that I show in the slide. Now, what other types of useful quantum learners can we find? Well, a lot of people claim that we can do a lot of things, but the reality is that the more that we try to understand what's really happening and the assumptions that are going on, it's getting clear that obtaining those quantum speedup is really not as easy as we thought. The assumptions that people make to get quantum speedups, like sparsity of rank assumptions of matrices, those are rarely realistic, because once you make those assumptions, then even classical algorithms become easy. However, there has been some interesting progress. And in this case, what we want to do is we want to go beyond just heuristic without guarantees. We want to find algorithms with a provable upper bound on performance. So an example is the question, okay, so say that I have a machine learning algorithm that does only slightly better than random guessing, say because you're running it in a noisy device. Can we convert that weak and inaccurate algorithm into a strong and accurate learner? And there is a classical algorithm to do this. It's called AdaBoost, and it works by using the weak learner polynomially many times to obtain a strong learner. So at a high level, say that you have a class of functions that take X and output 0 and 1, say like a label red or blue on a set of points. Then for every possible distribution of the input state, if you receive a set of training data and then a new point Y, the weak algorithm classifies Y, so it tells you if it's red or blue, but it does so only marginally well. Right? The success is random plus epsilon, where epsilon measures the advantage over just random guessing. Now, if S is your training set and D1 is the uniform distribution on this training set, then run the weak distribution on that training set, and you produce a weak classification result. We call that a weak hypothesis. But because that was your training set, right? For every point in S, you know the labels, whether it's red or blue, and you can compute if that hypothesis was different from the actual red or blue labels in S. And that way, then you can build another distribution D2 based on where that hypothesis failed. So intuitively, what you're doing is in this distribution is putting more weight on where the weak algorithm failed. And then in the next step, you run the weak algorithm again on those points where the previous algorithm failed to force a good hypothesis to come out of that region. And you keep doing this T times and take a weighted majority. So in this way, you can obtain a strong hypothesis from combining all the weak hypotheses. Now, why is this attractive? Well, it's attractive because if you try to implement a strong algorithm on a quantum computer, it will probably become weak because of the noise in the device and because of other problems. So the question then is, can you boost a quantum algorithm with a classical AdaBoost? And the answer is yes. But then you want to ask, okay, so then what is the time complexity of AdaBoost? Meaning, like, how much time do I need to spend? Well, that time is proportional to what is called the VC dimension of the class, which is defined as the maximum number of data points that can be classified exactly in all possible ways. And the expensive step is that calculation of epsilon 1. Can we improve this quantumly? And the team found that yes, we can improve it quantumly. That if you do a quantum boosting, then you can improve the algorithm in square root of the classical complexity. So you have a quadratic speedup. You do lose in epsilon, but epsilon is inversely proportional to, it's an inverse polynomial in n, in the number of attributes in the data set, while the VC dimension could be exponential in the number of attributes in the data. So you lose in the polynomial parameter, but you gain a quadratic improvement in the exponential parameter. And the algorithm, as you can imagine, it can probably be improved further. Now this quadratic speedup might look like a trivial Grover speedup, but in reality it is highly non-trivial. The main contribution in this paper then was to give a robust ADA boost algorithm that even if your algorithm is not exact, but it just gives you approximations of what you want, and you have the problems of noise and so on, it still works. And then you can do a quantum algorithm on top of it to get the quadratic quantum improvement. Another example is statistical query learning. So suppose you get T copies of a coherent superposition of X and CX. Can you learn C? Well, theoretically, it has been established that there are certain sets of functions for which if you can generate coherent quantum superposition state, then with T copies of the state, you can learn the coherent quantum superposition quantumly exponentially faster than classically. Now, of course, you never get identical copies in quantum, that's impossible. And also we don't want to be performing a joint measurement on all the T copies because that seems pretty far away from what's achievable right now. So the question is, can we just do single copy measurements? Can we do measurements on a single copy of the state and then keep repeating that to get statistics instead of doing a joint measurement? And can we learn something that way? Now, since the results of the measurements are classical, what this implies is that we would be performing a quantum learning algorithm with classical outcomes. And what the team showed is that almost all quantum learning algorithms can be converted into this model. So they don't need entanglement measurements, and they can just be done with single copy measurements using a classical learner. And even if your state is noisy and you obtain noisy measurement statistics, you can still produce a good quantum learning algorithm. It's pretty resilient. In particular, you can use this framework to learn Hamiltonians. You can write the Hamiltonian as a sum in its Pauli decomposition or as a decomposition in terms of your favorite orthonormal basis. And so you're given T copies of the Gibbs states of the Hamiltonian and you can learn the Pauli coefficients up to an error epsilon. That's a lot. There is a lot of work in the literature about Hamiltonian learning problem. However, what was missing was that proper theoretical understanding of the complexity of the problem. And so here what the team showed was a provable algorithm that given order m cubed, many samples of the Gibbs state of a Hamiltonian on m qubits, it can learn the unknown quantum Hamiltonian. Now, in terms of implications, well, I would say that probably next steps, but it would be interesting to see if this can be used to say, like do tomography using single copy measurements. Okay, so now how do we optimize the circuits and reduce their complexity to run them on hardware, while maintaining their essence? And Dmitry Maslov and Sergey Bravy are leading research in this area. In particular, they studied circuits, Clifford circuits. Those are composed of phase, Hadamard, and control NOT gates. And as you know, these circuits are important for error correction, for randomized benchmarking, tomography of multi-qubit states, and a lot of other things. Now, while looking for an efficient implementation of any Clifford circuit, they show that any Clifford circuit on n qubits can be uniquely decomposed in a layer of Hadamards, followed by permutations on the n qubits, all sandwiched between Hadamard-free circuits. Doing that, and then using a polynomial time algorithm for computing the layers in the decomposition, you can execute an arbitrary n-qubit Clifford circuit in depth 9n. Now, one of the observation that led to this result was that if you have a Clifford circuit followed by the measurement of all qubits in the computational basis, then applying a Hadamard-free operator immediately before the measurement of all the qubits is equivalent to a simple classical post-processing of the measurement outcomes. And so one of the two Hadamard-free stages can be skipped in that case. Right? So you get, keep playing those games and you can get to the proof of depth 9n. Now, if you want to generate a random uniformly distributed n-qubit Clifford circuit, that was another result that they showed. The previous state-of-the-art algorithm to output that circuit had runtime on the order of n cubed. The algorithm described in this paper has n squared runtime. Here's another neat finding of this study. Take a look at that circuit and think about how many CNOT gates that circuit requires. And it is an optimal CNOT circuit, so it's a classical reversible linear circuit. And the answer is 7. So what happens is that you can introduce Hadamard gates, and then you can commute them with the CNOTs to turn some of those CNOT gates into control Z gates, and then induce those control Z gates via a set of phases so that you don't need 2-qubit gates to implement the control Z. So this shows that in certain cases, purely quantum gates like the Hadamard gate can reduce the cost of implementing Hadamard-free operators. So if you're only concerned with the number of entangling gates, then some linear reversible functions can be implemented more efficiently as Clifford circuits, as opposed to circuits relying only on the CNOTs. Now, this gain of using Clifford circuits over reversible CNOT circuits cannot be more than a constant factor. All right, so all these theory developments have to be integrated and their value proved in demonstrations, and those demonstrations need to teach us something valuable. It's not just about running something in hardware because we can, right? It has to be because they are a combination of computational capabilities possible using quantum circuits and inaccessible to classical circuits, or that they show how the tools and the techniques that we have developed are integrated and work to enable the solution of increasingly more complex problems, or both. And Sarah Sheldon is our lead for those demonstrations. Now here's the most recent example that demonstrated the use of a technique that was first introduced in the context of Hamiltonian simulation. It's called quantum signal processing, and used it to find the solution of symmetric Boolean functions under space-restricted computations. What that means is that the input is a read-only memory, and you can only compute on a restricted number of bits or qubits. And you can solve that problem more efficiently using quantum circuits than with classical circuits. So to describe the problem at a high level, you want to calculate symmetric functions of k bits. You have n bits, which constitute your computational space. So meaning that, in the case of the quantum circuits, you apply control U gates with the k bits as the control, and U operating over the register of the n bits. That's what we call limited space computation. And it turns out that if you restrict the computational space to 1 bit, then you cannot compute the Boolean symmetric functions classically at all. But a quantum circuit exists that does this with a single qubit of computational space in quadratic time, or I should rather say using n-square entangling gates. Right? So when the computational space is 2 bits, then Boolean symmetric functions cannot be computed classically in polynomial time. It requires exponential time, but they can be computed in quadratic time on a quantum computer. The simplest of these functions is to compute the 1 bit limited space, is the majority function of 3 bits. Then another example is the second least significant bit function. And as you can imagine, the gain that you get here is related to the fact that a qubit is more than just 1 bit or 1 piece of information, because it has phase information in it and you can leverage that. So now you might ask, why did we do this demonstration? Well, for several reasons why. One, because it is a problem that illustrates how a quantum bit stores more useful information for the purposes of a computation than a classical bit. So in that sense, it shows how quantum can be exploited to compute something that is incomputable classically in a model with restricted computational space. Second, because the quantum circuits are obtained using quantum signal processing, and to the best of our knowledge, I think that technique had not been demonstrated experimentally. And third, because it served to highlight how we tune up more complicated pulses, because executing the circuits efficiently require calibrating these custom entangling gates. So for example, you have a 2-qubit entangling gate and then have single qubit rotations added to it so that you can implement square root of C0, control S, and control HX. Now those are all locally equivalent to a ZX pi over 4 rotation. So that's in reality what is calibrated directly. And on top of that, it also incorporated the measurement error mitigation techniques that we saw earlier. So for the demonstration, we decided to restrict the computational space to 1 qubit so that we show maximal separation of quantum and classical. And so we define success by comparing to the maximal classical probability of evaluating the function classically using limited space computation. And that is the normalized distance of the truth vectors between the computable and the desired function. It's kind of analogous to an algorithmic success probability. It just measures the best that you can achieve classically. And for the 3 bits symmetric Boolean function, that is 7/8. For 4 bits is 81%. In general, for an n-bit symmetric Boolean function, the classical success probability approaches 1/2 for large n, but quantum circuits can implement it exactly using n-squared gates. And here you have the experimental results. The team developed 2 quantum circuits to compute the majority of 3, one with 8 entangling gates for which the quantum computer had success probability of 93%, and one with 5 entangling gates with success probability of 95%. So in both cases, this is surpassing the classical threshold of 88%. The majority of 4 is calculated with a circuit with 7 entangling gates that had 87% fidelity, above the 81% achievable classically. And the results of computing the second least significant bit function, where the quantum computation exceeds the best that you can do classically on all inputs for 3, 4, 5, and 6 Boolean bits. And now finally, let's look at some examples of using quantum circuits in applications and how clients contribute to this. This is work that is led by Stefan Werner in the Zurich lab. This is a good example of our team producing a result and the community in the Q network leveraging it and improving upon it. Right? The team in Zurich applied quantum amplitude estimation, which you can use to approximate the expected value of a random variable. So they apply it to the problem of analyzing risk and pricing securities, and they show that it does so quadratically more efficient than the Monte Carlo simulations that people use to calculate these things. Value at risk is this example, is one of the example of these metrics that are used in risk analysis. It quantifies the level of financial risk that you have in your portfolio over some period of time. Say that, you know, if you're told that you have a 3% 1-year value at risk of 5%, it means that you have a 3% chance of your portfolio decreasing 5% in value over a year. And the team showed that if you take the shortest possible circuit depth, the calculation converges with the inverse of the number of samples to the power 2/3. That's faster than the scaling of Monte Carlo, which is the square root of the inverse of the number of samples. But if you can afford to let the circuit depth increase, then you can get a convergence rate approaching the inverse of the number of samples. And that's a quadratic speed up over Monte Carlo in terms of the number of samples needed for convergence. The plot that you see there on the right, those are the results in one of our devices of finding the value today of a 0 coupon treasury bill that is discounted at a given interest rate, assuming that in the next time step, there will be an increase there might be an increase in that interest rate. It compares the convergence of the error of the Monte Carlo simulation to the quantum algorithm with respect to the number of samples. The quantum algorithm starts with a larger error, but for 16 samples, which corresponds to 4 sampling qubits, it already takes over Monte Carlo. So now say that you wanted to calculate the 99.9% confidence level value at risk for a portfolio of 1 million assets. I'm changing the notation here a little bit to give confidence level, but what I mean is then you have a 0.1% chance of experiencing undesired losses. You can do the estimate of the resources that computation would take, and you see that if we need 1 million qubits, able to do 10 million T-gates, we better find ways to do more efficient error correction, like we talked about before, and ways to optimize those circuits. Now, after IBM published that first paper on quantum risk analysis, our colleagues at Keio University and their collaborators at Mitsubishi Financial Group and Mizuho found a way to improve the resources. They developed a quantum algorithm that only requires to run that lower part on the quantum computer and then replace the rest by a maximum likelihood estimation. So we call this the maximum likelihood amplitude estimation. And it leads to a significant simplification of the quantum circuits in terms of reducing the number of qubits and the circuit depth. But that maximum likelihood amplitude estimation is heuristic, so it doesn't have any rigorous convergence theory behind it, though it did show good performance in empirical studies. The problem is that the maximum likelihood estimation part gets numerically challenging for increasing accuracy. Then motivated by that Keio paper, Scott Aronson and Patrick Roll showed that it is possible to achieve comparable circuit reduction combined with a rigorous theory. Their algorithm, it achieves optimal asymptotic scaling, but it comes at the cost of having a very large constant, so that makes it impractical. And we call that the quantum amplitude estimation simplified. Then based on those results, the team at Zurich then developed an algorithm that leads to simplified circuits, has a rigorous convergence theory, performs good or better than the others, and does not involve any numerical challenging steps like the maximum likelihood estimation. And those algorithms were implemented in Qiskit and compared on a simple problem, a fair coin. The log plot that you see there shows the resulting estimation error with respect to the required quantum samples or oracle calls. So in quantum amplitude estimation simplified, the constants are so large that it requires even more samples than classical Monte Carlo for the target accuracies that were tested. Iterative quantum amplitude estimation is as good as the maximum likelihood amplitude estimation, and both of them not only simplify the circuits involved, but they also lead to a better performance than the canonical quantum amplitude estimation. Then later on, JP Morgan, working with us, used these methods together with error mitigation to price a European call option. And you might say, okay, well, but you know, European call options are easy to calculate. And that's true, but this illustrates how all of these methods come together to solve practical applications, and then you can expand from here to consider truly complicated options like things that depend on the path followed by the asset over time. Now here you can see how the results improved using the gate error mitigation that we talked about. And this is really a story, you know, from the first quantum risk analysis paper to the improvements made by Keio and the incorporation of the error mitigation method, of how much momentum there is in the field and how everything comes together, and how much value you can get from being part of an ecosystem where the members are building on top of each other, you know, to drive progress. So then this is an overview of what we still need to do. In the near term, we have to continue scaling up error mitigation and improving the systems, then optimizing the circuits to reduce 2-qubit gate counts. From there, we start implementing error correction, and there will be probably a period of coexistence of error mitigation and error correction, where, for example, you could use some error mitigation techniques to reduce resources in some of the error correction processes, while you get then to the error corrected systems that we need. For that, we need to get the error rates below threshold, and then we need to find more efficient codes. And now circuit optimization should focus on reducing non-Clifford gate counts. We talked about that demonstration of signal processing in symmetric Boolean functions. There will be a demonstration of water coming up by entanglement forging. The fact that it's water here is not important. What's important is the technique of entanglement forging. But you know, I'll leave that as a teaser. That paper should come out before the end of the year, probably probably beginning of next year. So stay tuned for that. And I think that you know, that this is the team again, all the leads for all this work, and then of course there's many other contributors that I couldn't name them all. With that, I thank you for the time and your attention, and take some questions.
Let's thank Zaira again for a beautiful talk. There we go.
Yes.
Apologies, Zoom was going over time. Any questions for our speaker? Please go ahead.
It was a lot of information at once.
We were following and taking notes. Maybe then I can start with one question. So you have mentioned in this machine learning algorithms that it's quite difficult in principle to find applications where you see a large speed up. And of course, there's also these new classes of quantum-inspired classical algorithms with L2 norm sampling. For example, Edwin Tang, looked at with Scott Aronson's Netflix problem, etc. So really what I was trying to ask is, are there cases where we could expect an exponential increase? Because even with this quadratic increase, there's a lot of overhead and that goes into this, but are there cases where we may even expect in machine learning domain some kind of exponential increase?
Yeah, I mean, like we're studying, cases where we can expect that. I guess like the paper that I gave the reference, okay, so there's a caveat to that. So I gave the reference to Chris Santem's last paper in the archive where he proves, finds a feature map and a kernel that can do classification that quantum cannot do. So there you have that type of big advantage. Your classical fails, you cannot do it. You can do it with the quantum circuit. However, because that solves the discrete logarithm problem, you need short for that. So that's the caveat in here, right? Like algorithms that we find that can give you those big advantages are in the fault-tolerant regime.
That's right. So basically the Gen 1, if you like, at least for as far as I understood it, this machine learning algorithms, you're just still searching a matrix, right? And there's still the difficulty of either executing a Grover-like search or actually creating the quantum RAM state that actually has to load, and all of these things basically reduce your advantage to a polynomial or square root at best.
Yeah, for some, yes. In this case, in the case of these quantum kernels, you don't need that. That was the point. The point was developing an algorithm that you don't need QRAM, that you don't need quantum data, that you can just the input is, you input classical data, you output classical data, and then you're using the circuit to map it. Because then what that allows you to do is it allows you to level, like, you have fair game now. You have, the data is classical, so you can run your classical algorithm, you can run your quantum algorithm, you can compare. You don't have to be, using this QRAM.
That's right. You need Fourier transform under the hood, right? And if you can get that into your machine learning algorithm, then you should have all the benefits of and pains of implementing that circuit. All right.
And pains. Yes.
Very good. Other questions for Zaira? Okay. David, you have a question for Zaira?
I do not, because she actually practiced the talk with me before. So, so everything was clarified. I don't even remember what I was confused about when we practiced.
I wanted to make sure that people were going to be interested in the topics.
For the group, I directed Zaira's thesis, so we know each other.
Yeah.
Very good. All right, no worries. Final call for questions for our speaker. All right, if not, let's thank her again for a wonderful talk, telling us about all the different, Jean-Luc Ville, you are coming in.
So yeah, maybe I have a question, but I'm sorry, we'll be a bit more on the technical side. So yeah, no, I mean the technical qubit side, like a bit less algorithmic part. You show these graphs of all the qubits. Do you know how many different physical frequencies are used? Like I know that on your the one where you have several qubits and then they are connected by one qubit and then it's another one. So I think you are using the same frequencies on these different circles of qubits, right?
Yeah, so if you mean, so let's take, for example, the Heavy-Hex, right? Lattice that we have in our system. It uses 3 different frequencies.
So it's just 3 different frequencies. So you have like 64 or more qubits.
That was the motivation actually for going to the Heavy-Hex, that, if you have the square lattice and you're trying to, well, we're thinking also error correction here. If you're thinking about something like the surface code, you need 5 different frequencies. But we have the problem of frequency collisions. So we wanted to decrease the number of frequencies, different frequencies.
But
and
so
this lattice allows you to have only 3.
And on your system, so you have your 64 qubits, like the qubit on this circle, which has, let's say, the frequency A, and the qubit on the neighboring circle, which also has frequency A. If you drive this qubit, you get nothing on this qubit at all. You get no crosstalk at all between the different circles.
If you have, oh, you mean like between one check and another check?
Yeah, one of these circles of qubits.
Yeah, so there is some crosstalk. So, you know, in these circuits is part of what we're investigating, like how do we, I mean, okay, you have two parts in here. You have the hardware team trying to lower, you know, all of these errors as much as you can, but then you also have the theory team trying to make these circuits resilient to crosstalk. And they found, I didn't talk about this, but they found a way in which they believe they can make circuits fault tolerant to crosstalk.
Ah, so you kind of take into account the fact that driving a pulse on this circle, you will get something on the other one.
That's right. So so I showed only in the logical error rate simulations, I only showed the same error for everything, and I didn't take crosstalk into account. The team is doing simulations with realistic noise taken into account, and so they include coherent errors and they include crosstalk, and they see how it behaves if you add crosstalk, if you add coherence errors. And then, you know, then they adjust the code and the circuits to be able to handle those.
Because I thought it was a bit counterintuitive to use exactly the same frequencies on these different, because what we see on our chip is that we get a huge crosstalk if we are close in frequency. So, but okay, yeah, the engineering team is trying to reduce that, and you are also taking that into account for designing your algorithms.
Yes.
Okay, thanks. Yeah.
Okay, very good. Any final questions then for our speaker? Okay, if not, let's thank Zaira again for a great talk and look forward to catching up with you in a different venue.
Thank you, Irfan.
Okay, thanks everyone.
Thank you, everyone.